Start by finishing the lecture from yesterday, where we were doing a calculation in JT gravity of z of beta 1 times z of beta 2. And I've written here, just to remind you, the action for JT gravity and consists of these two terms that will be, both of them will be important today. The first one in brackets here is a topological term. It's proportional to the Euler characteristic. And today I'm going to normalize the coefficient in front of it by writing it as S naught divided by 4 pi. This big S naught was previously called n times little s naught. So in the relation to SYK, this parameter S naught is proportional to n. It's extensive. It's the zero temperature entropy. Okay? And then we have the usual second term that you guys are familiar with by now. I'm also going to differ a little bit from previous conventions. I've rescaled beta and the energies in order to remove some numerical factors because out of some feeling of responsibility, I'm actually going to try to write the correct numerical factors in at least some cases today. It's not that they're important, like the factors of 2 and things are very important in Nati's lectures. They're not very important conceptually in these lectures, but they do work out. Anyhow, so we were discussing this product of partition functions, z of beta 1 times z of beta 2. And we discussed two contributions. So one contribution to it consists of two disconnected geometries. Here we have a disk where we have a little region of the disk with boundary of length beta 1 over epsilon. And we have the same one for the second factor of z of beta 2. And the contribution to the product of these partition functions here is e to the 2 times s naught times the product of the Schwarzian partition functions for the two theories. And you can see that the numerical factor in the exponent is a little bit simpler than previous days because I've absorbed a factor of like n over j into beta. Okay, so this was one contribution. And we had just started to discuss the second contribution. So here we have a connected manifold. Remember that in Joukiev-Teitelbaum theory, after integrating over the dilaton phi, we have to consider only spaces with constant negative curvature, r equals -2. And you can indeed find a space like this with constant negative curvature. I've written the metric for you here, d rho squared plus cosh squared rho d tau squared. And tau is the direction going around this geometry with the topology of a cylinder. And it has periodicity by a parameter b, which will be a parameter of this geometry. So there isn't just one geometry like this. There's a one parameter family of the geometries labeled by the periodicity of tau. So geometrically what that is it's the size of the minimal geodesic that goes around the geometry, which sits right here. Anyhow, in order to compute a quantity like this, we study this geometry here, and we put a cutoff boundary on the left side with length beta 1 over epsilon, and a cutoff boundary on the right side with length beta 2 over epsilon. And the analysis of the path integral in this space is somewhat similar to here. We have to do a path integral over the wiggly boundaries, a wiggly boundary on the left and a wiggly boundary on the right. And in getting this result, we use the fact that the path integral of the Schwarzian theory is one loop exact. This is a slightly different Schwarzian theory. The action for the wiggly boundary on this manifold is a little bit different than for these disks, but it's also one loop exact path integral. And I've written the result here. So the contribution from the wiggly boundaries factorizes into a contribution from the left and a contribution from the right. Those are these two factors here. Now, the quantity in the exponential is just the, it's the action of the classical configuration, which would be a circle, an unwiggly boundary. It has the opposite sign from the classical contribution in the case of the disk, and that traces back over here. The classical contribution comes from this term here, the extrinsic curvature term, evaluated on the circle. And if you evaluate the extrinsic curvature in this geometry, you find that it's a little bit less than 1 instead of a little bit more than 1. So we have a negative piece in the exponential. And that piece depends on this parameter b. Okay, and the denominators here are the one-loop determinants. The one-loop determinant is, again, slightly different than in this case, but it's straightforward to work out. It is proportional to 1 over square root of beta instead of 1 over beta to the 3/2. The most important feature of this quantity is that there's a 0 times S naught, because the Euler characteristic of a cylinder is 0. So here the Euler characteristic of 2 disks was 2. That was this factor of 2 here, multiplying S naught. But the Euler characteristic of the cylinder is 0. So this topological term contributes nothing to the to this term. Okay, so the final thing that we have to do in order to evaluate the contribution of this is we need to integrate over the length of this minimal geodesic. We have a 1-parameter family of these geometries, and we need to integrate over them. And the correct measure for this is this measure here, b dB. We'll discuss a related measure in more detail later, but it can sort of be motivated as follows. You can imagine taking 2 different wiggly boundaries here, and we could take a fixed configuration with 2 wiggly boundaries, and we could rotate one of them relative to the other. That would give us a new configuration. Now, the amount by which we can rotate is b. Well, it's at least proportional to b. And actually, in the correct measure, it turns out to be equal to b. So the integration measure has a factor of b in it for that reason. We have an integral b dB of this, the product of these 2 factors. And that integral is easy enough to do, and we get this expression here. Okay.
How do you know the measure doesn't depend on temperature?
How do we know what, sorry?
So the argument that you give does not determine the dependence on it does.
Oh, the fact that this was proportional to b? Or yeah, the actual argument for this is not quite as simple as I said. The actual argument for this measure factor here is that the JT path integral reduces to an integral over these hyperbolic manifolds with a particular measure on the Weil-Petersson measure. And that's what this factor is here, b dB. We'll discuss the Weil-Petersson measure in more detail later, but this is a very simple case of it. Okay. Well, this? Well, yeah, it is. So, but it's a huge simplification of the original path integral. So that's because the JT theory is so stupid. Like we start out by doing a path integral over phi and the metric, but the integral over phi localizes us to these constant negative curvature spaces, and we just don't have a huge variety of them. What we have in this topology are this space here, and we have just a few things to integrate over. One is the shape of the wiggly boundaries, and the other is the length of the minimal geodesic. So the original path integral has reduced, after doing the integral of these wiggly boundaries, to just an integral over b. Okay, so now let's see what these contributions look like if we analytically continue the beta parameters to z of beta plus it times z of beta minus it. And let's take t to be large. Then this first contribution gives us something which is proportional to e to the 2s naught. For large t, we get a 16 pi, this factor doesn't matter for anything, times t cubed. This we had already discussed yesterday. It gives the initial slope region. And it's related to the fact that the density of states of this theory vanishes like a square root of energy at low energies. Okay, and the second term gives us something that's like t divided by 4 pi times beta. And this is the promised ramp contribution. It's growing linearly in time, and actually the coefficient here is the correct coefficient that you would predict from random matrix theory. So I want to emphasize that from the perspective of gravity, this term here is a non-perturbative effect. It is a much smaller, well, for reasonable times, this is much smaller than this term. This term is proportional e to the n, e to the 1 over g Newton. Okay? So this is a very small effect, but for very large times, it dominates over the first term. Okay. So this completes the discussion of this the slope and the ramp in the Joukiffe-Teitelbaum gravity theory. Yeah.
I was going to ask, are we imagining like t is much greater than beta when we write this?
Yes, in writing this expression instead of this expression, I assume t was much bigger than beta. So this arrow here means t is much bigger than beta. Okay, yes?
The analytically continued version of this geometry, is it the traversable wormhole or what is it?
Yeah, okay. That's a good question. So the question is here we did some analytic continuation of the answer, but we can ask what is the analytic continuation of the geometry itself. And I can draw a picture of that for you for the case where t is large. When t is large, looks like the following. So here we had our ADS2. It's actually, for very large t, this is almost a piece of the real anti-de Sitter geometry. So the Lorentzian anti-de Sitter geometry. And so we had a geometry for the thermal field double state that looked like this. Here are our boundaries on some trajectory like that. And what this geometry corresponds to is taking a periodic identification of this Lorentzian space. A periodic identification under a time translation that acts like a boost. So it would be an identification from some surface here to some surface here, where the difference of these guys is t. So t is the time difference between the two identification surfaces. So if you take this geometry and identify those surfaces, you get something that looks sort of like a double cone, like this. So that's the geometry that one has. And this geometry actually one can consider for general black holes. So this is a way of arguing that for general black holes, you have a contribution that's proportional to t. And that's good because this ramp feature, this linear growth in t, is supposed to be very universal, shared by almost any interacting theory.
Just to clarify this won't be traversable, right? You can't.
No, it's not. And it's quite an unphysical geometry. The periodic identification in real time is a very funny thing. Okay, yes?
So, I mean, is it that somehow they're getting this geometry is somehow not captured by Gaussian saddles? I mean,
No, this is a saddle. So this is it's a saddle point of the gravity theory, and it just has much smaller action than, it gives a much smaller contribution than the original saddle point, the naive saddle point. Yeah. There were a couple other hands. Yeah.
Yeah. Suppose I take this two-level statistic that the Altman and company derive, and I compute this z times z. What would be the correction? Just to get the feeling as to if the level statistics is different, where would I see that?
I think, so you're asking about calculation in the SYK model?
Yeah, there's some conjecture or motivated conjecture. What's the level, the two energy level statistics?
Yeah, in the SYK...
It's basically a random matrix theory plus a correction.
Yeah, I think in their analysis, the corrections are things that decay exponentially in time t. So they found a linear ramp like this, and actually in SYK you can find similar saddle points, and they give again the correct coefficient from the perspective of random matrix theory. And they were arguing that there are a set of exponentially decaying corrections to that. So actually we could give a bulk interpretation of exponentially decaying corrections like that by considering some matter field propagating on this geometry, and those give exponentially decaying corrections. Yeah.
When t is much bigger than beta, the second term is the leading piece.
No, it's if t is much bigger than like e to the s naught over 2, that the second term is bigger than this one. Yeah.
So, I mean, is there any way to guarantee that there won't be any higher order terms in t over beta which doesn't overwhelm the first term?
No, and this is a good question. So that leads me to the next the next topic, which is an obvious failing of our analysis so far, which is that we have this slope region and we have this ramp region, but we do not have the plateau region. And the explanation of the plateau seems to be much more complicated. It's not related to any particular geometry like this. What it seems to be is a sort of doubly non-perturbative effect associated to a asymptotic series of terms like this. So just to emphasize, this term, from the perspective of ordinary G. Newton perturbation theory, this term is a non-perturbatively smaller correction than this. However, the plateau seems to be associated to the fact that we have actually an asymptotic series of terms like this. And that asymptotic series has itself non-perturbative effects associated to that series of non-perturbative effects. And that seems to be the explanation of the plateau. So what today's lecture is going to be about is this series. So we're going to discuss a relative of this series in Joukiev-Teitelbaum gravity. And so I'm changing gears to that now. And there's an important conceptual remark to make, which is that yesterday we motivated the discussion of this ramp and slope and whatever and random matrix theory based on the idea of random matrix universality, that we were going to try to look at something which applied to almost any interacting quantum system. In particular, it should be true for black holes. And this ramp is an example of that. But today we're going to discuss something which is not of that type. We're going to discuss details of this series in JT gravity that go beyond the random matrix universality limit. In other words, we're going to be looking at statistics of eigenvalues in JT gravity which are not close together necessarily in the spectrum. Because there's this sort of funny fact, which will be the main point of the lecture today, which is that JT gravity doesn't just agree with random matrix theory in this universal limit, like you would expect SYK or a black hole or like the 3D Ising model or whatever to do. It agrees with the random matrix ensemble on the nose. So it's precisely describing a random matrix ensemble. So from that perspective, it's very non-generic. We don't expect other gravity theories to behave that way. But it's convenient for understanding this series and trying to ultimately understand the plateau. So that's what we're going to do today. Before I start discussing JT gravity, though, we have to another thing I should mention is that the lecture today is not in published work. It's work in progress with Steve Schenker and Phil Sott. And as a type of preparation, before we discuss JT gravity, I'm going to need to discuss some more aspects of random matrix theory so that we'll recognize a random matrix ensemble when we see one. So I wrote an equation like this yesterday, but the definition for our purposes of a random matrix ensemble will be an integral over matrices with a weighting like this, where H is L by L matrices. And we discussed yesterday how one can study this thing at large L, and the eigenvalues form a distribution, which we wrote as rho naught of lambda. This distribution can be determined in terms of the potential, V of H. So one way to specify the particular random matrix ensemble we're discussing would be to give the function V of H. Then at large L, we would compute this leading density of eigenvalues, rho naught of lambda. But another perspective, which will be more useful for us, is we could specify this function, rho naught of lambda. And then we can find a potential, V of H, such that the random matrix integral with that potential will have this leading density of eigenvalues. So it will be convenient to go in that direction, because we're going to start with information about this function rather than starting with information about that function. So yesterday we discussed matrix integral using this method of orthogonal polynomials, which is a very powerful method for getting some exact or nearly exact results. today we're interested in a somewhat different perspective. We're interested in the genus expansion, a 1 over L expansion of a random matrix integral. And for that purpose, a somewhat different technique is useful that we'll discuss in a moment. But the types of observables that people discuss in this context are, in the random matrix literature, are often correlation functions of resolvents. So let me explain what those are. So the types of observables that people like to study in 1 over L perturbation theory are observables like this. Correlation functions of n or k or whatever, some number of these En minus h. These are called resolvent operators, trace of 1 over energy at some parameter minus the random matrix. And actually, it's convenient to consider not this correlation function itself, but the connected part, where we subtract off products of lower order correlation functions. Now, observables like this in pretty much any observable in a random matrix integral has a 1 over L expansion, which is related to the a 't Hooft double line expansion of this integral. I'm not going to go into that in detail, but I'll just tell you that this expression here has an expansion which looks like the following. We define some functions R of g comma n, functions of the n energy arguments, divided by L to the power 2g plus n minus 2. Okay, and these coefficient functions here give the coefficients in the 1 over L expansion of these resolvent correlators. So this is a fact about these random matrix integrals. And actually, something that will be important later is that we shouldn't write equals here. We should write some kind of lesser equals, because this is not a convergent series. This is an asymptotic series. So g is going from 0 to infinity, and it's referred to as the genus. It would be the genus of the 't Hooft double line diagram that would give this contribution. Okay, so how does one calculate these expansion coefficients for these correlation functions of resolvents? There are, again, many methods that have been used in the literature. This is a problem that's been studied for a long time. And the method that we'll discuss briefly today is based on what are called the loop equations. And this goes back at least to work of Migdal. But the loop equations are based on the following. We can write that 0 is equal to the derivative, the integral of the derivative of something, where the something that we pick will be will be this expression here. So it's 0 because we're integrating a total derivative. So it looks like a sort of trivial equation, but if you distribute the derivative over these terms, and you use this 1 over L expansion of the resolvents, and then you collect terms of a given order in 1 over L, then you get a recursion relation that determines higher genus resolvents in terms of higher genus functions like this in terms of lower genus functions like this. Now that sounds good, and it is good, but actually it's sort of complicated to analyze these equations. And one of the reasons is that when the derivative acts on these terms, it gives us terms involving products of resolvents, but it also acts on this potential here. And it gives us terms where we have things like trace of the potential of H divided by E minus H. And that quantity isn't one of these quantities. So the recursion relation doesn't obviously close on the set of variables that we want to study. So you have to be clever in order to actually get a set of recursion relations based on these loop equations. And people have been clever in different ways in the literature. And these quantities were computed for the first few orders using different clever techniques by many different groups of people. But there was a significant advance in like the mid-2000s, I think it might have been 2007 or something like that, when Einard showed how to really simplify these loop equations into a very concrete recursion relation that I'll write a special case of in a moment. Yeah.
Can you just say what the input for the recursion is?
Yeah. Okay. Yes. Yeah. Thank you. It's actually a good thing for me to say. So the input for the recursion relation is just this function here, rho naught of lambda. So it's clear that that rho naught of lambda determines everything about the matrix integral because it determines the potential, and the potential determines everything. But it's true in a more direct way that the recursion relation will start with a term that's basically this function here. And we'll see that in a second. And the recursion relation will not depend on the potential except through this function. That's what will make life nice. Okay, so this is one piece of background, and I haven't really shown you the equations here, but I'll show a version of them in a minute. Another piece of background is the following. What we're going to be interested in is trying to apply this philosophy of these recursion relations to compute the expected random matrix statistics for a theory that resembles JT gravity. And what resembles means is it has the rho naught of lambda function of JT gravity. So what is that function? That's the function that we get by interpreting the leading contribution to the partition function. Z of beta was e to the s naught times e to the pi squared over beta. So this function that we had on the board a moment ago, interpreting this guy as an integral over energies e to the minus beta energy times some rho naught of energy. And okay, we can solve this equation by doing an inverse Laplace transform of this function. And we find rho naught of energy is equal to e to the s naught divided by 4 pi squared sinh of 2 pi squared of e. So we also had this function yesterday, and we commented on the fact that it vanishes like square root of energy for low energies. So what we would like to do is run the matrix integral recursion relations starting with this function, and then compare to what we actually get in JT gravity. But yes? These things? Yeah. Oh, yeah, sorry. These are just parameters. Okay. So this thing is a function. This is a function of some n arguments, e1 up to en. And it's given by the expectation value in the random matrix ensemble of this quantity, where e are the arguments and h is the random matrix that we're integrating over. These things, no, they're just arguments of the function, so they're whatever you want. Actually, yeah, the first time you see these resolvent quantities, they look funny because, like, what if e was one of the eigenvalues? Then what would this thing mean? And it's a good idea to define these by giving the arguments of the function a small imaginary part, or more generally considering them somewhere in the complex plane that's not on the real axis where the energy eigenvalues live. And then this expression is well defined. More generally, what we find is that this function is not a single valued function of the energies. It has a branch cut, which runs over an interval of the energy axis where the eigenvalues live. Yeah?
If L is finite, we also have a cut?
Yeah, so if L is finite, then we have in some ways, it's a nicer situation. We have two different entire functions. Actually, I think I learned this in a paper that you wrote. So the two entire functions are based on taking, let me call R one of these operators for resolvent. Well, different R than this one. But, OK, let me just write it. If we take trace of E plus or minus I epsilon minus H, and we look at the exact expectation value of, let's say, just this quantity in the matrix ensemble, then we get a different function if epsilon is positive or negative. We get two different functions. Both of them are entire functions. And that's the structure at finite L. OK.
That the bracket is really this rho naught, rho of even, rho of E2, so on, inserted in the top right?
Yes, and then divided by Z. So the normal way that we do expectation values in ensembles. OK.
So L in that expansion is the total dimension of the Hilbert space, right?
The dimension of the matrix,
Yeah,
the
so
random matrix H.
But for you it's e to the S0 rather than e to the S0 integral over the stage.
Yeah, I haven't said what L will be in our case, and that's coming. Yeah,
But you don't have, you can't regulate this somehow with the finite dimension of Hilbert.
Yeah, that's literally what I'm going to talk about next. So just let me say it. Although, let me insert one comment which I forgot to say earlier, which is another thing. If these resolvents are bothering you, then and also because what would be more natural to compute in JT gravity are these partition functions, but you can go back and forth between them because if we take trace of e to the minus beta h, multiply it by e to the beta e, integrate it over beta, then we get trace of 1 over e minus h. So we can go back and forth between the resolvents and these partition functions. Trace of e to the minus beta h is what we've been calling, well, that's z of beta. OK, so we can use either set of variables. In the matrix integral community, people like to consider these correlation functions of the resolvents. But in JT gravity, it will be more natural to compute z of beta, and we'll have to use an integral transform to go between them. OK, so let me now come to this comment about how we're supposed to realize something like a matrix ensemble that gives us this leading density of eigenvalues. And an objection to it that was raised a second ago is that this sinh of energy is not a normalizable, sinh of squared of energy is not a normalizable function. So this wouldn't make sense as a leading density of eigenvalues for something with a finite number of eigenvalues. However, we can realize that function by taking a limit of ordinary matrix integrals. So let's plot this function, sinh of square root of energy. It looks something like that. We can't quite get a matrix integral that has this leading density of eigenvalues, but we could get one that has this, or we could consider another one that gets something like this, or like this, and so on. And as we move between them, we'll have to increase L. We'll have to increase the dimension of the matrix because we're trying to reproduce a function with a larger integral. So we'll have to increase L. And in the limit, where we're trying to reproduce this function, we'll have to take L to infinity. We'll have to take L to infinity, but we'll focus on the part of the spectrum sort of near the left side, and we won't worry about the thing that happens very far to the right. This procedure of taking L to infinity and focusing sort of near one edge is known as a double scaling limit. And it's a way of achieving densities of eigenvalues sort of like this. So the most famous example, well, I don't know, one famous example of a double scaling limit is when you're trying to get the density of eigenvalues e to the s naught times square root of energy. And this one's a little bit easier to get than this one. You can take, for example, the Gaussian matrix integral, which had this semicircle form, near the edge of the semicircle, it behaves like a square root of energy. So you just take the semicircle, make it big, add a bunch of eigenvalues, and focus on the left side, focus on the low energies. And that's a way of getting this function. And actually, these double-scale matrix integrals are in many ways much simpler than the other matrix integrals. It's not, the reason they're simpler is not because L has gone to infinity, therefore the genus expansion collapses just to the first term. The genus expansion is still non-trivial, but instead of being a 1 over L expansion, it becomes an expansion in 1 divided by the density of eigenvalues in the region that you're studying. So it will become an expansion, it can be organized as an expansion in powers of e to the minus s naught. So that's the structure that we should be looking for in this case. We should be looking for an expansion in powers of e to the minus s naught. There's another comment about this double scaling limit, which is that in practice, to achieve this density of states would be quite complicated. We would have to take L to infinity, and we would have to tune the potential in some way so that we get this sequence of successive approximations to this sinh of square root of energy function. And in the limit, the potential actually diverges. The thing that's finite is the effective potential, which is the sum of the potential plus the effect of all of the other eigenvalues. But fortunately, we don't care about the potential, because our philosophy will be that we write everything in terms of this density of eigenvalues rho naught of e. And we'll use a recursion relation that doesn't care about the potential. It depends on this function, rho naught of e. OK. So now I think I can write the recursion relation, this Einard recursion relation for the genus expansion of a matrix, specialized to the case of a double-scaled matrix integral like this one. So that looks like the following. It's discussed in the literature in terms of variables, and I apologize for this, that are slightly different than these r, g, comma, n variables. Instead, it's discussed in terms of w, g, comma, n, which is a function of some parameters z1 through zn. These parameters are related to the energies of the resolvent correlators. So there's some simple rescaling here, but the relation is basically w is equal to one of the expansion of the resolvents with the energy arguments given by minus the z squared arguments. Technically, the reason that one does this, or why one prefers these functions to these functions, is that, as I said before, the resolvents and their correlators are not single-valued functions of energy. They're double-valued functions. But if we define things in terms of z, then it's single-valued. So these functions w are nice functions. They're single-valued functions of z.
The fact that you end up with an asymptotic expansion has to do with this regularization procedure of completing the distribution and then getting rid of parts of it?
No, that's true even for an ordinary matrix integral. Okay. So, so this is how these WGN quantities are defined, with a couple of exceptions. When G is 0 and n is 1 or 2, we have a different definition. So let's look at this one first. This is the first function, and it's given by 2 times z times y of z, where y of z is related to the density of eigenvalues, rho naught of minus z squared. Okay, so I apologize for all of this notation. Okay, it's what it is. For the case that we're interested in, where we have this sinh of square root of e density of states, this function y of z is sine of 2 pi z over 4 pi. And already here you can see an example of this fact that in the z coordinate, the function is single-valued. We had this sinh of square root of e, which is a double-valued function of energy, but in terms of z, it's single-valued. Okay, and the other special case is w 0, 2, and that's given by 1 over z1 minus z2 squared. All right, and now this is the recursion relation. This is just a processing of these loop equations that I wrote before. And it's a somewhat clever processing of the loop equations. This residue trick is a way of dealing with the fact that you had some unwanted terms in the recursion relations that involve derivatives of the potential. You have, the way the argument works is you write the answer as a contour integral, and then you deform the contour, and you argue that those terms involving the derivative of the potential don't contribute singularities. So we can drop them. And then we get a recursion relation just in terms of the quantities that we like. So it's a recursion relation that has somewhat complicated structure. I can discuss this more if you like, but maybe it's simpler just to give one example. So the simplest example is, suppose we're trying to compute W1, 1 of Z1. So first of all, what is that? That's related to the resolvent 1, 1. The indices 1, 1 mean that, first of all, we're looking at just a single resolvent. So we're looking at trace of 1 over E minus H. And the fact that the first subscript, the G subscript, is 1 instead of 0 means that we're going to be looking at the first non-trivial term. So this thing would be equal to R0, 1 plus times e to the s naught plus e to the minus s naught times R1, 1. So we're computing the first non-trivial term in the e to the minus 2s naught expansion. Okay, and for this special case, this second term involving this sum doesn't contribute. The only thing that contributes is this term. We have to substitute in g minus 1 and n plus 1. So in that case, we have to look at w0, 2. w0, 2 is this expression here. And we evaluate it at the point z minus z. And I've evaluated this expression there. We get 1 over 4 z squared. The factor pi over sine 2 pi z is this factor, 1 over 4 y of z. And y of z is given here. So if we calculate the residue of this expression, then we get this simple rational function of z1. And in fact, all of these expressions, with the exception of this one, are rational functions of the z's. Okay, so this is all I wanted to say about the genus expansion of a matrix integral. And it sets our expectations for what would define a random matrix integral with the leading density of states given by this sinh of square root of energy expression. If we wanted to say that JT gravity was precisely a random matrix integral, then what we would have to show is that in JT gravity, these resolvent quantities have an expansion in terms of a set of coefficients that satisfy this recursion relation. Okay. So yeah, maybe I'll cover this up. And now we'll move to actually try to understand this in JT gravity. So we discussed this disk contribution in JT gravity, and we discussed another contribution involving two boundaries. But to make our life simpler, what we're going to focus on, at least to begin with, are the computation in JT gravity of single boundary quantities. So we're going to try to compute z of beta. Yeah, sorry. We're going to try to compute z of beta in JT gravity. The first term is this one. But according to this discussion, we should have an infinite series of corrections, weighted by powers of e to the minus s naught, powers of e to the minus 2s naught. Now, in JT gravity, the integral over the dilaton imposes that the metric has to have uniform negative curvature. So whatever we're doing, we need to find a collection of geometries that have uniform negative curvature. But there are plenty of geometries that have, well, we need to have a boundary of some length. We need to have constant negative curvature. There are plenty of geometries like that. So schematically, what they look like would be, you can have a geometry like this. You can have a geometry like this, and so on, with more handles. So this one has genus 1, this one has genus 2. We can have arbitrary genus G. And what I've drawn is just the topology of the surface. But in fact, you can put constant negative curvature metrics on these geometries with this topology. So one comment before we analyze them in more detail is that these geometries are actually not solutions. They're not classical solutions to Joukiev-Teitelbaum gravity. So we have two classical equations of motion. One comes by varying the dilaton. That's satisfied here because r is equal to -2. There's another equation that we get by varying the metric, and that gives us an expression which is something like, I'm not going to get the right coefficients here, but there's 3 terms like this. And this equation turns out to imply that the geometry has a killing vector. The killing vector is this vector. And that implies that the geometry has to have a symmetry. But these geometries do not have any symmetry. So it's not possible to solve this equation on these geometries, which means that there's no classical solution of JT gravity with this topology. But we're not just in the business of considering classical solutions. We're trying to do the path integral of JT gravity. And these things will contribute to the path integral, even though they're not classical solutions. Okay, so
So what is the justification to keep those and ignore non-classical solutions?
oh, you mean things that weren't? Are you asking why we're restricting to constant negative curvature things? Yeah, it's because the condition that r was -2 was not just a classical equation of motion. It was imposed by a Lagrange multiplier. So the integral over the dilaton really imposes a delta function that r is equal to -2 in the path integral. So it's a special case where the classical equation of motion is imposed as a delta function. The equation for the dilaton that we get by varying the metric, this one is not imposed in that way because the metric doesn't just enter the action linearly.
But then you could take others looking for the dilaton not on with objects which don't have higher genera?
Well, I think if we're looking for orientable surfaces with one boundary, then these are all that we have. This is the complete set of the topologies that we have, and we need to discuss the integral over the metrics with this topology. But we'll do that, and we'll do that exactly. So that's the philosophy. We're going to do this path integral exactly.
The disk is a solution?
The disk is a solution, yeah. But although I didn't comment on it, this one that we discussed earlier today, the cylinder with 2 boundaries, that was not a solution. Because, well, for basically the same reason that these ones aren't solutions. Although that does have a symmetry, but it's still the same reason.
Sorry, so how do you think that these topologies are inconsistent with the symmetry?
Well, there's just no symmetry of this object. There's no like U1 symmetry. Yeah. Okay, so let's first think about the contribution of this topological term for these geometries. So the Euler characteristic of this guy is 1. So we get a factor of e to the s0. The Euler characteristic of this thing is -1. So we get an e to the minus s0. And this is e to the minus 3 s0. In general, we get, well, the disk, which is sort of special, plus a sum genus equals 1 up to infinity of e to the 1 minus 2g times s0 times something that I'll just call zg of beta. So zg of beta will be the integral over this thing without including the topological term because we've already included it explicitly in this prefactor. Yeah, that's coming. It's coming. So
Sorry.
yes.
You wouldn't include things that have two boundaries whose length sum to beta.
No. No. The boundary condition is that we have a single boundary and it has length beta over epsilon. Okay, so let's write a formula now for, I want to have more space, so I'm going to erase this. Let's write a formula for ZG of beta. So I'll write a formula and then we'll explain all the terms. Looks like an integral b db from 0 to infinity of e to the minus b squared over 4 beta over 2 square root of pi beta times v comma 1 of b. So let's look at the terms. First, let's look at this one here. This is the same factor that we had before when we were discussing this space with the cylinder. That's because, take this geometry here and cut it at this point. The stuff to the left of that is just the same geometry that we had for 1/2 of that cylinder. And this factor here arises from an integral over the wiggly boundary we have at the edge, which is described by a Schwarzian theory. It's the same Schwarzian theory that we had in the case of the cylinder, and so we get exactly the same factor. This is the classical action, and this is the one-loop determinant, and it's a one-loop exact integral, so that's the whole thing. Now, what is this term here? This term is the volume of the moduli space of this piece. So we cut here along some the minimal geodesic that separates the asymptotically ADS region from the topology. And as an intermediate step, we fix this to be of size b. So we fix this geodesic to be of length b. As you see here, we integrate over b at the end, but for the moment we fix it. We do the integral over the Schwarzian, and we should also do the integral over the moduli of the Riemann surface that we have here. And more precisely, it's the volume of the moduli space of a Riemann surface with a geodesic boundary of length b. This is sometimes called a bordered Riemann surface. And what the volume means is it's the volume computed with the measure that's induced by the JT path integral. And that measure is the Weil-Petersson measure. This can be worked out using sort of, by gauge fixing and including ghosts, and seeing that the determinant from the ghosts cancels against the determinant from the phi and the conformal factor. Or it's actually easier to see this using the first order formulation of JT gravity, which is a BF theory. And in general, these BF theories reduce to an integral over the moduli space of flat connections with the analog of the Weil-Petersson measure. So in our case, the moduli space of flat connections corresponds to these geometries. And the integral over that space with the Weil-Petersson measure is this function here. This is just a name for it. So let me say a little bit more about what this Weil-Petersson measure is and how one can parameterize the moduli space. The idea is that we would like to build up a surface like this from simpler constituent parts. And the construction that's used is to build it up out of building blocks like this, where this is a hyperbolic manifold with 3 boundaries of lengths like b1, b2, and b3, which are geodesics. This is called a pair of pants. And what you can do is you can glue these things together in order to form a surface like this. But in doing the gluing, you have some integration variables. One obvious integration variable is the length of the geodesic here. So I'm going to glue this one to another thing here, which is connected to some other pair of pants. And we need to integrate over the same geodesic length, but that's an integration parameter. So that's one coordinate. Another coordinate is the relative twist. So we can take this thing and we can twist the other one and then glue them together. And the Weil-Petersson form that determines well, it's a symplectic form on this space, is a sum over all of the things that we glue together of, so that's an index I, of dB, dBi, wedge, d tau I, where tau I is the length of the twist measured in units of the hyperbolic radius. So,
Can you get any of these endpoints from the G sigma, such that you know that it's SYK, not just some artificial truncation to J?
yeah, this is a good question. The only one that, well, so first of all, the problem is that they're not saddle points. So they're not classical solutions to G and sigma. And the G sigma path integral is more complicated, so it's not as easy to say our philosophy is we'll evaluate the path integral exactly and then like make sense of them. It's too complicated a path integral to do that too, so I don't know exactly how to search for the relevant configurations. An exception to that is the analog of this cylinder that we discussed earlier, and in that case you actually can find these configurations because you can study a related quantity where there are honest saddle points, and then you can solve the equations. But in the G and sigma path integral, I think that there should be configurations sort of like this that are not exactly solutions, but nevertheless contribute in an important way to the path integral. However, let me qualify what I said by re-emphasizing that the discussion that we're having here, where this thing will end up being a random matrix ensemble on the nose, is not true of SYK. It's true of JT gravity, but JT gravity is not equal to SYK. They differ in several ways, and JT gravity is a good approximation of SYK for certain quantities at low energy, but it's not a good enough approximation that the fact that JT gravity as a random matrix ensemble implies SYK as a random matrix ensemble. And in fact, we know that SYK does not exactly have the statistics of a random matrix ensemble in the sense that we defined it. Yeah?
When you glue it, I'm a little bit puzzled. So you have a boundary condition on the length here, and you do the functional integral. Then you have some boundary condition of the length here, and you do the functional integral. And then you glue them, and you say that the length is the same.
Yes.
And you integrate over the length.
Yes.
It's not clear to me that this is the same as doing the functional integral over smooth surfaces. Because I can imagine many surfaces that have fixed length. Could I explain why, or is it complicated?
Well, we're not really even doing a functional integral anymore. We're just integrating over these hyperbolic manifolds. And so we're integrating over smooth hyperbolic manifolds, and those can be constructed by gluing these things together with the same length, and the only parameter that you have is a twist.
Oh, so that's because you impose this constraint strongly.
Yes. Yes, we've imposed r equals -2 as a delta function. Well, we didn't impose it. The dilettante imposed that. No, the dilettante is gone. We integrated over the dilettante. It says r equals -2, and then we never talk about it again. So, okay, so this is the... Yeah, we don't care about the equation of motion because it's gone. Okay. So this is the symplectic form, and to compute the volume form on this space, you take e to the omega. And then you, in principle, do the integral over these twists and the lengths. But this is a really complicated thing, because a simple construction where you build this thing out of a single pair of pants construction will overcount the actual moduli space, because you can construct the surface from different pairs of pants, and a single pair of pants will actually be constructing precisely the same Riemann surface multiple times as you vary these b and tau parameters. So it's a very complicated story to actually evaluate these volumes. And there are papers where, long papers where people write down coordinates for the moduli space. They make sure that they're not overcounting, and then they do the integral with this symplectic form. And they get simple answers in the end. Like, for example, v1, 1 is it's this expression. It's a polynomial in b squared, in b. In general, these volumes are always polynomials in b of degree, I think it's 6g minus 4. But they're complicated to evaluate from this definition. However, one last thing I should explain, now I can explain it better, is that this factor here, BDB, is just an example of this, where tau is the twist and it runs from 0 to b. That gives us this factor, and then we integrate over b. So this part here should also be considered as part of the integral over the moduli space. Oh, one other comment I should also make is that you can see from this expression already that it's not a classical solution, because it's not stationary with respect to B. So it's not stationary with respect to this perimeter. So the action has a direction. It wants B to get small and this thing to sort of degenerate. But we're not going to let it. We're going to integrate over the full range. Yeah?
And do you need to worry about the divergences coming from the boundary of the moduli space that happens in higher divergences in string theory, for example?
Yeah, here it's convergent. So
And how do you say that you don't have divergences from the boundary of the moduli space?
well, which boundary are you worried about?
Moduli, for example, on a torus, there are higher divergences coming from the boundary of the moduli space, this PSL2Z moduli space, for example.
Yeah, well, I'm not sure what to say except that these quantities are all finite. So you integrate over the full moduli space and you get a finite answer. They're finite, but they're difficult to calculate. Yeah.
Integral over B does remain finite?
Integral over which B? This B?
Yes.
Well, yeah. So this is some polynomial, and this is a Gaussian. So it's we're in good shape. Yes.
So you integrate B until infinity, isn't it? B until beta over epsilon?
Oh, yes, but we take epsilon to 0. So this theory is defined by a limit, where we fix the length to be beta over epsilon, and then we take epsilon to 0. But it's an interesting question. If you keep epsilon finite, can you do a version of this? And it looks like it's significantly more complicated for, among other things, the reason that you said. Okay. So this is our expression. Now, we have an infinite series of these terms corresponding to the surfaces with arbitrary genus. And what we would like to claim is that these expressions give precisely what we would have predicted based on the random matrix recursion relation. So to check that, what one is supposed to do is study, instead of this partition function, study these resolvent operators. So we should go back to the resolvent. Actually, better, we should work directly in terms of this W variable, wg, 1 of z. This is 2z times the integral d beta of e to the minus z squared beta times z over beta. So this expression here gives the resolvent evaluated at energy equals minus z squared. And we multiplied by 2z because that was this factor that appeared in the definition of W. So we can look at this expression, and then we can put this formula for z of beta in. And so let me put this in. Integral b db e to the minus b squared over 4 beta over 2 squared pi beta vg, 1 of b. And now we can do the integral over beta. The beta dependence is in this term, and this term here. And that gives an integral. So this factor of 2 here cancels this factor of 2. The integral over beta gives a factor that's e to the minus z times b times square root of pi. Square root of pi cancels this square root of pi here. The 1 over z cancels this factor of z here. And in the end, we get this expression. Okay, so this would be the W quantity instead of the Z quantity. Okay, and now the punchline of this is that these quantities do indeed exactly satisfy the recursion relations of the matrix integral, and they satisfy it with the with this function, y equals sine 2 pi z over 4 pi. And this is a very non-trivial fact in mathematics. And it relies on this work of Miriam Mirzakhani, which she won the Fields Medal for, which was finding a recursion relation for the volumes of these bordered Riemann surfaces, the Weil-Petersson volumes of these bordered Riemann surfaces. So she found a recursion relation for that thing. It's based, very vaguely on building higher genus surfaces up by gluing together lower genus surfaces. And basically, she solves this problem of the overcounting in a clever way that I don't fully understand. So she writes a recursion relation for these volumes. And a little while later, it was observed by Einard, or I think it might have been Einard and Oranten, that if you take the Laplace transform of the volumes that she considered, then the recursion relation that she wrote down becomes the recursion relation of the matrix integral. Actually, they don't always think about it as a recursion relation of a matrix integral. They think of this type of recursion relation as a structure that they call topological recursion. And it's related to many families of invariants in mathematics. And they showed that by Laplace transforming Mirzakhani's recursion relation, that these quantities here satisfy precisely this recursion relation, and they find this function, sine of 2 pi z over 4 pi. And it just so happens that that function is also related in this way to the density of states, leading density of states of the Schwarzian theory. So that implies, without any further work, that these geometries in JT gravity give precisely the e to the minus s naught expansion of random matrix statistics.
And this works for any number of boundaries.
It works for any number of boundaries. So, yeah, as an example, it works for so an example of a geometry that we fortunately don't have to compute would be this one, with like 3 boundaries or 17 boundaries or whatever, and a bunch of handles. And this statement implies that this thing gives precisely what you would expect for the 3 partition function or 3 resolvent correlation function at genus 2 in a random matrix integral. Okay. Sorry? Did you say L? Oh, yeah, that's the number of boundaries. So this is so n. Let's go back and remember where n came from. N is this argument here. It's just the number of arguments of R, and this R g comma n was the expansion of the n resolvent quantity. So this was something with, right? We had trace of 1 over e1 minus h times trace of 1 over up to trace of e n minus h. Yeah, that's right. So, exactly. So we can do an integral transform of this thing to get to work instead with something with z of beta 1 up to z of beta n. So that's what this n thing is. It becomes z of beta 1 up to z of beta n becomes the number of these asymptotically ADS regions in the geometry we're considering. So this is n equals 3. Okay. So
Was there another reason for now to assume that this is related?
Wait. Yeah, they don't actually think of it as being related to a matrix integral. They think of this. So they think of the Mirzakhani recursion relations as being an example of topological recursion. They also think of matrix integrals as being an example of topological recursion. But as far as I know, it hadn't. The interpretation of the Mirzakhani volumes as being related to a matrix integral hadn't really been discussed. JT gravity sort of gives you the function that you need. It gives you this function that you need to, which relates the Weil-Petersson volumes to like z of betas or to resolvents. So and it's sort of non-trivial. It involves the integral over the Schwarzian out at the boundary of this asymptotically ADS region. So that's, well, yeah. Okay. So let me now comment on one other thing. I don't have time to discuss this in detail, but this series here, this genus expansion, is an asymptotic series. It's an asymptotic series because the volume of moduli space grows rapidly with g, like 2g factorial. This is a fact that's familiar in the discussion of string perturbation theory, where the fact that string perturbation theory is asymptotic is because of the same growth of these volumes of moduli space. And the asymptotic nature of string perturbation theory is related to the existence of these d-branes, quantities that are like proportional to e to the minus 1 over g string. So in this language here, that would be things that are proportional to e to the minus e to the s naught. And essentially, the plateau in the spectral form factor is one such feature. And this isn't a new observation. It's been understood in the matrix integral literature how to go from low orders in the genus expansion to understand the non-perturbative effect that gives you the plateau. An analogy from string theory would be that in order to understand the d-brane effects, we don't actually have to compute like very high orders in string perturbation theory. We can get by with just studying like the disk amplitude and maybe the annulus amplitude. We need to study low order amplitudes in order to understand the physics of the d-branes, and in that way we can treat the non-perturbative series. The analog of that in the matrix integral is that you study a quantity. You study a quantity instead of the resolvents or this zg of beta. You study a quantity which is the determinant of some parameter, energy, minus the matrix. And those determinant operators are related, well, they've been related in previous literature to insertions of d-branes. And if you use the determinant operators to calculate the spectral form factor, then you find this plateau in addition to the slope and the ramp. So this was not a very good explanation, but I don't have time to do a better one. And it's not really so much new to JT gravity anyhow. It's something that's been discussed in the context of matrix integrals in the past.
When you're saying matrix integrals, you're only considering the trace m squared potential? Or
No, an arbitrary potential v of m. So it's important to take some kind of complicated potential in order to get the density of states that we need for the Schwarzian theory.
But there is another contribution. Okay, that's maybe something we may expect. But how does it kill the linear increase? What's the mechanism which stops the increase? What saturates here, in other words?
Well, the simplest way I know of doing the calculation doesn't make the answer to your question very clear. The simplest way of doing the calculation is, instead of calculating z of beta, we calculate the pair correlation function, the density of states. And the goal will be to get this sine kernel expression that we discussed yesterday and that gives the ramp on the plateau. The determinant operators can be used to calculate the correlators of the density of states. And from them, you can get the sine kernel. And if you then integrate that, you get the ramp on the plateau. But that's a somewhat convoluted path. It isn't as simple as just saying we take these things and then we add one other contribution and it cancels what we had and adds the plateau. It's somewhat more complicated chain of logic. I can try to say more about these determinant operators, but there's something else that I'd rather comment on. So maybe I'll try that. The discussion we've been having from the perspective of quantum gravity looked reasonable. We were just integrating over these geometries. We said we have a couple of boundaries, and we should include geometries that connect the boundaries together. That sounds reasonable from the perspective of integrating over metrics. But these types of contributions are quite unreasonable from the perspective of ADS CFT. So this is a puzzle that's been going for a while. The reason why they're unreasonable is that in familiar examples of ADS CFT, we think that the partition function that's involved is the partition function of a specific quantum mechanical theory. Like n equals 4 superconducting nulls with n equals 37 or whatever, and like a particular value of the 't Hooft coupling. There's a particular Hamiltonian. It has a set of energy levels. The partition function for fixed beta is just a number. And in that setting, it doesn't make sense to have a contribution. It doesn't make sense to have a contribution like this, which contributes if we're calculating z of beta 1 times z of beta 2, but that wouldn't contribute if we were just calculating z of beta 1 separately. In other words, this type of contribution gives us a non-factorizing answer, where this is, we have to invent some notation with brackets. This thing is not equal to z of beta 1 times z of beta 2. Now this is fine if z of beta is the partition function of a matrix and we're considering an ensemble average over matrices. So that was the perspective in the discussion of SYK, in the discussion of random matrix theory, and we sort of got led down this path of thinking that it was reasonable in Joukiffe-Teitelbaum gravity. But this type of thing would not be reasonable in a more conventional ADS CFT setup, where z of beta is just a number, and it's not an element of a probability distribution. And this is impossible. So this discussion has been had in the literature before, and it goes back to work of Coleman on geometries similar to this, which are referred to as Euclidean wormholes. And in the ADS CFT literature, it's been discussed by Maldacena and Maus and by Arkani Hamed, Orgera, and Polchinski. What are you supposed to do with configurations like this? Since they seem to give non-factorizing contributions to the partition function. And I don't have anything helpful to say about that at all. I don't think this story sheds much light on that problem. It seems like a serious problem, that something we're missing. The most obvious prescription would just be you shouldn't integrate over them. Like in gravity, we just shouldn't integrate over geometries like this that connect multiple boundaries together. We shouldn't include them in the quantum gravity theory. And that sounds sort of reasonable, but the funny thing that's happening here is that geometries like that aren't just giving us some random non-factorizing answer. They're giving us a particular kind of answer, like a very reasonable answer for a random matrix ensemble. So it's as though, at least Joukiffe-Teitelbaum gravity, which is a well-defined theory of gravity, it's not dual to a specific quantum mechanical system. It's dual to an ensemble, an ensemble of quantum mechanical systems, and in particular, a very rigidly constrained ensemble, one that satisfies the rules of random matrix theory. Yeah?
Would it be a problem to say that the ensemble averages in relative theory are dual to time averages in the random matrix?
Well, that would be reasonably okay, because time averages, that's right. So we could do some integral over time parameters here or something, and then we would not need to get a factorizing answer. But we're not doing an integral over times here. We're computing z of beta 1 times z of beta 2, and we're studying them for fixed beta 1 and beta 2. And
In the ensemble level.
no, there's no, I don't understand the proposal, I guess. Could you explain it more?
Instead of doing an ensemble average, you can have it be a time average, right? Summing over all these geometries is just the same as the time average. And then you don't have to invoke this ensemble.
Yeah, okay, so I'm interpreting your comment as saying that these non-factorized contributions would be okay if we were averaging over time instead of averaging over disorder. And that's true to some extent, but we're not averaging over time, so we still have the problem. We know if we're averaging over time. If we're averaging over time, we're doing an integral like dt of beta plus it z of beta minus it. So it's true that this quantity here doesn't have to factorize. but that's not what we're computing. We're computing this with fixed beta parameters, and then in a standard ADS-CFT setup, it should factorize. Yeah.
Didn't we hear from Igor that there is a version of the SYK model without the density sum?
Yes, and for that theory, well, I don't know how to calculate these spectral form factor quantities. For one thing, it doesn't have a large N action formulation. But if we were able to calculate it, we would presumably find some kind of, for the spectral form factor, for this quantity in that theory, we would presumably find something that looked like this, and then it had this kind of erratic behavior. We wouldn't find something like what we find in JT gravity, where we have a smooth curve here. And so JT gravity would not be a reasonable description of that theory. Yes?
Do you have a reason to believe that pure JT gravity does not have a single CFT dual described in papers by Daniel Harlow and Daniel Jeffress? Would you expect to similarly find a dual as some ensemble average in, say, pure AS3 gravity?
Oh, I think in ADS3 gravity there's a bigger problem, which is that, as far as I remember, the density of states actually is negative in places. I'm not 100% sure if that's true, but I think that was a conclusion in the paper by Maloney and Witten. And if that's true, then you can't interpret it as a disorder average. It's just not okay. So, yeah, so, well, okay. Okay, I'm pretty much out of time, and I don't want to embark on another discussion at this point, so let me just stop here, and thank you very much.
So if you just look at JT gravity but impose that you only have a single boundary, then why doesn't it make sense to interpret that as a specific field theory without any disorder?
Well, it would, but the function that we get, for example, the density of states that we get is a continuous function of energy. And that's not acceptable from the perspective of a quantum mechanical theory. It needs to be a sum of delta functions. So from that perspective also, by the way, a continuous function of energy is fine for a disorder average of quantum theories. So even from a single boundary, we can sort of conclude that JT gravity wants to be a disorder average rather than a specific quantum system.
Yeah, please.
Can you comment on potentially including punctures on this complex Riemann surface? Would that correspond to some sort of local operator still in pure JT?
Why would we include punctures?
Because it's something you can do, but it's not a reason.
Okay. Yeah, we would include punctures if we had, like, well, I'm not sure. We could include some objects with, I don't know, some instantons in the bulk with some tension or something that would be associated to conical excesses or conical defects, and we could integrate those over space. Yeah, there are more complicated moduli spaces that we could imagine integrating over. Another example would be if you take the bulk theory and add some topological field theory or add bulk matter fields. And that probably breaks this topological recursion and might break more than that, but it might be something to explore.
Please.
So if you compute something using topological recursion, can you compare it to something? Can you compare the answers that the topological recursion gives you to JT gravity, some calculation in JT gravity?
Yes, that was the point of the lecture. That the topological recursion tells you what a random matrix ensemble would predict for these partition functions or resolvents. And you can calculate them in JT gravity, you get exactly the same answer. So I'm not sure if you had a different comparison in mind.
So I missed a few minutes here. Unfortunately, it seemed important to be oriented. You discussed matrix model, and I want to recall what is the relation between the matrix model you described here and the one that appeared at the late 80s in the context of non-critical string theory.
Yeah, well, there were a few of those, and so those were associated to. Yeah, this is an important point. The discussion that we had here is, in many ways, very reminiscent of of a previously known famous connection between random matrix ensembles and theories of gravity. For example, there's a relationship between Liouville gravity and a particular matrix integral. This is the C equals 0 matrix model. And there are other varieties of this involving Liouville coupled to minimal models, or other bulk theories. One difference is that here the connection to something like gauge gravity duality, where we have these asymptotically ADS boundaries, is clearer. So the observables that we're studying are more familiar in that context. So in other words, here we're really studying something which is like a Euclidean black hole and small corrections to the Euclidean black hole.
Where is it reflected in the matrix model?
Well,
Difference.
Well, the matrix model is quite different. I don't know
No, so I want
which.
to recall what, I want you, if you can, remind me what is the difference.
Okay, so in that case, the density of states of the matrix model is something which just has some like power of energy vanishing. So it's a simpler function. And here we have this sinh of square root of the energy. It's a more complicated density of states. So
So it's a different thing.
yeah, they're related in the sense that they're double-scaled limits of single Hermitian matrix integrals, but they're different. You know, that's a wide variety of different problems, and there are quite different elements of that class.
I have a follow-up question on that. Does this correspond to a particular point in the space, or is double scale matrix potential?
Yeah, it would.
So that means that if so, it should be a particular two-dimensional field theory on Liouville gravity.
But it might not be it's probably not a conformal field theory.
It's always a conformal field. You mean not the conformal field
'Cause-
theory coupled to gravity? The combined system is always.
Yeah, I think it's probably not a conformal field theory coupled to gravity.
So what?
But, well, no, I'm not saying that's a bad thing. I'm just saying that means it wouldn't fit in the set of things that had been studied.
No, it was studied.
Okay.
All the massive deformations between all these minimal models were studied.
Okay.
So which point is it?
Well, I guess it's a pretty complicated point. For example, this thing can be defined in terms of another framework that sort of includes this and includes that and many other things is the Kontsevich integral. And that thing is parameterized by a set of these times, which are related to the parameters that you're discussing. And this is a point there where you have like an infinite set, like all the times turned on in some particular set of coefficients that gives you this sign of 2 pi z over 4 pi. So,
But if it describes one of these points, it has deformations which are all the others.
yeah, I don't understand what those would correspond to in the bulk. Yeah, you would like to start with JT gravity and move a little bit in some direction by adding some bulk matter fields or something to JT gravity, and I don't know how to do that.
Well, you just told us something. You write it in terms of a point in the space of T's, and then you define the space of T's.
But we don't have a very good bulk description of a generic point. So we have a bulk description of this sort of weird point. There are bulk descriptions of some other points, and maybe those other points, maybe you can explain to me, but perhaps, I don't know whether the flows between those other points also have a nice bulk description. I guess they do in terms of the flow of the CFT that you've coupled to gravity. But I don't know how to connect in the bulk this point to those.
So the thing that is missing is the stuff that you have to add to JT gravity to describe these deformations.
I guess so.
On the matrix model side, it's clear what needs to be added.
Yes, but yes. It's sort of weird that there is a point like this where the metric is just rigid. Like there's, from the perspective of these triangulated surfaces, the metric is fluctuating. And it's weird that you can somehow go to a point where the metric is not fluctuating. It would be nice to understand, how you move away from that point.
No more questions. This is the last lecture in this cool and serious, very nice lecture by Douglas. So thank you very much for.
Thanks. Thank you.